So in this lecture, we start a new chapter on symmetric operators. So let me start with a definition. And here, I will be considering a Hilbert space. So X will be, in this lecture, a Hilbert space over a field which is always represented by K. And we will consider operators, A, defined on X. But let me start with an operator which is not bounded. So this operator might be defined only on a subspace of X. And I will represent by dA the domain where the operator A is defined. So A will be a linear operator from dA to X. And here dA, it's a subspace of X, so a linear subspace of X, which might be different from X. And dA will be called the domain of this operator. Well, the definition is the following. So assume that I have A, an operator which is defined on dA, which is a linear, so let me insist on that. This is a linear subspace of X. So suppose that A is such an operator. I'll say that A is symmetric. So I'm defining a symmetric operator if two conditions are satisfied. The first one is that this set dA is dense. And the second one, B, is that for all x and y elements of dA, we have that the scalar product of ax with y, it's equal to ax to x ay. So I have a linear operator. So let me mention that, let me insist that A, it's linear. And it's defined on a linear subspace of X. I will say that this operator A, which is defined on its domain D of A, is symmetric if these two conditions are satisfied. So D of A, it's dense. So it's a linear dense subspace of X. And for all x and y in dA, we have this relation. So if these two conditions are matched for a linear operator A, we'll say that A is symmetric. And in this lecture, I will study properties of bounded symmetric operators. So let me recall X, it's a Hilbert space. A, it's a linear operator defined on a domain D of A taking values in X, which I'm assuming to be symmetric. So let me define now eigenfunctions and eigenvalues. So I will say that lambda in K, it's an eigenvalue of A if there exists x different from 0 in X, such that A of x, it's equal to lambda times x. So I'll say that lambda, so it's an element of the field K, it's an eigenvalue of A, if we can find x in X different from 0, such that A of x, it's equal to lambda x. And x, it's called the eigenfunction. So let me prove the main properties of the eigenfunctions. So proposition. So A from dA to X is a symmetric operator. So notice that I'm not assuming A to be bounded, just symmetric. So the first claim is that AX X belongs to the real for all x in dA. So if I take the scalar product of ax with x, well, this in principle, it's an element of K. Well, what I'm claiming that it's actually an element of R. So let me prove that. The proof is almost trivial. So since A, it's a symmetric operator, ax, it's equal to x ax. This, by definition, of symmetric operator. On the other hand, if you remember, one of the properties of the scalar product is that if I take xy, this is equal to yx if I take the complex conjugate. So remember, if I have a complex number, a bar represents its conjugate, and we have these properties of the scalar product of a Hilbert space. So if I apply that property to this expression, this is equal to ax x complex conjugated, and therefore this identity is telling me that the complex number ax x is equal to its complex conjugate, which means that ax x belongs to R, as I claimed. So my second claim is that if you take lambda in K an eigenvalue, then actually lambda is a real number. Well, the proof of this claim is also straightforward. So let me take lambda an eigenvalue. This means that there exists x in x different from 0 such that ax is equal to lambda x. Therefore, if I take lambda x x, well, on the one hand, by linearity, this is equal to lambda xx. On the other hand, since lambda is an eigenvalue associated to the eigenfunction x, this is ax x. Since A is a symmetric operator, this is equal to x ax. Now, as lambda it's an eigenvalue, this is equal to x lambda x. And by the property, the skew symmetry of the scalar product, this is equal to the complex conjugate of lambda, lambda bar, times xx. So now if you look at this sequence of identities, what we proved is that lambda minus the complex conjugated of lambda times the norm of x squared, it's equal to 0. And since x is different from 0, we get from this identity that lambda is equal to its complex conjugated, which means that lambda indeed belongs to R. So the third claim of this proposition is as follows. Take two eigenvalues, lambda 1 and lambda 2, eigenvalues of A, and assume that lambda 1 is different from lambda 2. So consider the eigenfunction associated to lambda 1 and the one associated to lambda 2. So let's take x1 and x2 different from 0, such that axj it's equal to lambda j xj. So x1 is the eigenfunction, one eigenfunction associated to lambda 1, x2, one associated to lambda 2. And what I claim is that they are all orthogonal. So x1, x2 are orthogonal. So if you have eigenfunctions associated to different eigenvalues, they need to be orthogonal. Well, the proof, it's also straightforward. Let me take lambda 1, x1, x2. By linearity of the scalar product, this is equal to lambda 1, x1, x2. Since lambda 1 is the eigenvalue associated to x1, by this property, this is equal to a x1, x2. Now, since A is symmetric, this is equal to x1, a x2. Now, since x2 it's an eigenfunction associated to eigenvalue lambda 2, this is x1, lambda 2, x2. Now, lambda 2 it's an eigenvalue, so it's a real number. And by linearity of the scalar product, this is lambda 2, x1, x2. So what we obtained from this sequence of identities is that lambda 2 minus lambda 1 times the scalar product of x1 with x2, that this is equal to 0. And since lambda 1 and lambda 2 are assumed to be different, we obtain that the scalar product of x1 with x2 is equal to 0, and this is exactly what we claimed. So we proved here that if you have two eigenfunctions associated to different eigenvalues, then they are orthogonal. The last claim is the following. Assume that we have a basis x1, x2, and so on, that this set forms an orthonormal basis of x, and assume that they are all, these xj are all eigenfunctions. So I'm assuming now that the space X has an orthonormal basis made of eigenfunctions. So let me call lambda 1, lambda j, the eigenvalue associated to the eigenfunction xj. So this means that lambda j xj, it's equal to a xj for all j. So these are the eigenvalues of the eigenfunctions xj. So I have a countable family of eigenvalues. Well, maybe they are all equal. I'm not assuming that they are different. Now let's assume that mu, it's an eigenvalue. And what I claim is that then mu, it's equal to lambda j for some j. So what this claim is saying is the following. Well, assume that you have an orthonormal basis of x made of eigenfunctions, then the eigenvalues associated to the elements of this basis are all eigenvalues. So if I have one eigenvalue, it must be equal to one of these eigenvalues. And again, well, the proof, it's very simple. Assume that mu is different from lambda j for all j. So I'll get a contradiction out of this. So I'm assuming that mu is different from all lambda j's. And let me call y the eigenfunction associated to the eigenvalue mu. So this is telling me that a mu, it's equal to mu, a y, sorry. It's equal to mu y. Since mu is different from lambda j, for the previous property, what we know is that y, it's orthogonal to all xj. On the other hand, since x1, x2 forms a basis of x, and it's orthonormal, I can write y in this base. So I know that y can be written as a sum for j larger or equal to 1 of theta j xj. So this means you have to remember from the lectures on Hilbert space that if I take the partial sums, what I get is that this is a sequence which is converging in the norm of x to a vector which I'm calling y. So since x forms a basis, I know that I can write y as this sum, which might be finite if there is a finite number of elements, or an infinite sum. And as I said, y is the limit of theta j xj. And here the theta j I didn't say, so let me say theta j are scalars. And y is the limit of this partial sum. Well, but so this means that the norm square of y, which is equal to the scalar product of y with itself, it's also, since this sequence is converging to y, this is also the limit. So okay, let me write this is y, and this is also the limit as n tends to infinity of y 1 up to n theta j xj. And by linearity, I can write this as the limit the complex conjugate of theta j, y xj. But y xj, it's y it's orthogonal to xj, so this is 0, so this sum is 0, and from that we conclude that the absolute value, the norm of y, it's equal to 0, because all these partial sums are equal to 0 because y it's orthogonal to xj. And from that we conclude that y it's equal to 0, which is a contradiction because I'm assuming that y it's an eigenfunction associated to mu, which means that y is different from 0. So I obtained a contradiction by assuming that mu is different from all eigenvalues lambda j, which means that if mu it's an eigenvalue, it must be equal to some lambda j. So up to now, I assumed that A it's a symmetric operator. So remember, A to be symmetric means that D of A it's dense, and that AX y it's equal to X AY for all X y in the domain. So we have a linear operator A defined on a linear subspace, which is dense, and that the operator satisfies this identity. Now I will add one property. I will assume that this operator is also bounded. Well, since A it's bounded, this means that we can extend A to the whole space. Right? A is defined in principle in a domain, which might be different from X. But by assuming that A is symmetric, we know that this domain is dense. And since A is defined on a dense subset of X and A is bounded, it can be extended in a unique way to X. So now I'm assuming, so without loss of generality, or more precisely, any symmetric bounded operator can be defined in the whole space X. So from this point on, I'm assuming that I have a linear operator A, which is bounded and symmetric, and therefore it's defined on the whole space X. So remember that the norm of an operator A is defined as the supremum over all x in x whose norm is equal to 1 of ax. Now, the proposition which I want to prove is that assume that A is bounded and symmetric, and what I claim is that we have an alternative formula for the norm of A, is that the norm of A can be also written as the supremum for all x whose norm is equal to 1 of ax x. So I want to prove this identity for bounded symmetric operators A. There is one inequality which is pretty clear. So let me denote by M this supremum. And what I want to prove now is that M is equal to the norm of A. Okay. There is one inequality which is simple to prove, is that M is less or equal than the norm of A. So let me prove that. So let me fix x such that the norm of x is equal to 1. Then I know by a Schwarz inequality that ax x it's less or equal than the square root of ax xx. Since the norm of x is equal to 1, this expression is 1, and what remains is the norm of ax. So I proved that this inequality holds for all x whose norm is equal to 1. So if I take on both sides of this inequality the supremum over x whose norm is equal to 1, on the left-hand side, what I get, it's exactly M. And on the right-hand side, what I get, it's A. So this proves that, indeed, M is less or equal than the norm of A. So we proved that M is bounded by the norm of A. What I claim, that actually they are equal, and this is what I will prove. So we are proving this proposition. Remember, A is a symmetric bounded operator defined on a Hilbert space X. We define M as the supremum over all x with norm equal to 1 of the absolute value of the scalar product of AX with X. And what we want to prove is that M is actually equal to the norm of A, where, remember, the norm of A is given by this variational formula. We proved already that M is bounded by the norm of A. So what I want to show now is that the norm of A is bounded by M. So in order to prove that, so let's look at the variational formula. So let's consider the square of the norm of AX. So AX square, so I fix X in X with norm equal to 1. I consider the square of this norm, so this is equal to the scalar product of AX. And since A is symmetric, I can rewrite that as A square XX, where here what I mean by A square X is that A applied to AX. Now, in order to continue, I will introduce two new elements of X plus and X minus. So X plus will be equal to lambda X plus 1 over lambda AX. And here, lambda, it's a real positive number. And X minus, it's exactly equal to the same expression in which I replace the plus sign with a minus sign. So you see, if I sum x plus with x minus, I get 2 lambda x. So x, it's equal to x plus x minus divided by 2 lambda. And while if I subtract x plus to x minus, I get 2 divided by lambda ax. So ax, it's equal to 2 lambda, lambda over 2 ax, x plus minus x minus. So if I subtract this expression with this expression, what I get is that x plus minus x minus, it's equal to 2 times 1 over lambda ax. So by dividing, I get lambda over 2, x plus minus x minus. And this is exactly, I will use these identities in order to replace in this expression x and ax by these identities. So I have a, on the one hand, ax, it's equal to lambda over 2 x plus minus x minus, while x, it's equal to x plus x minus divided by 2 lambda. And for this means that I get 1 over 4. And now I'll just compute term by term what I get. So there are 4 terms. The first one, it's ax plus x plus, because the lambdas cancel. Then I get this term with this one, so plus a x plus x minus, and this appears with a plus sign. Then minus a x minus x plus, and finally minus a x minus x minus. So this is just what comes from the computation. I will continue by erasing this expression. And maybe let me write it here, the values of x plus and x minus, because I will need that later. So remember, x plus, it's lambda over 2 x minus 1 over 2 lambda x ax. And x minus, it's lambda over 2 x minus 1 over plus ax. And there are no 2's. Sorry. So now what I get from this identity, so let me consider these 2 terms. What I get from them is that A is symmetric, so I can pass this A to the other side, and then use the fact that by skew symmetry to take the conjugated. So this is equal to 1/4 of ax plus x plus, then plus ax plus x minus minus ax plus x minus the complex conjugated, because here I got ax plus x minus ax plus, and this gives me ax plus, minus ax minus x minus. And you see that these are all identities. So I know that I have here a real number. And what I got is that this real number here, if what appeared is that I have a complex number C minus its complex conjugated. So this complex conjugated here gives me a number whose real part is equal to 0, and we have just an imaginary part which is surviving. So this difference gives me a complex number whose real part is equal to 0. So if I consider only the real parts, and I know that this is real, what I get actually is that ax squared is equal to 1/4 of ax plus x plus minus ax minus x minus. So let me claim that again. I started from this quantity. I made some computations, and I arrived at that this real number is equal to this sum, 1/4 of this sum. So we have seen in the previous proposition that this is a real number. This is a real number. And here we have a complex number minus its complex conjugate. So what I claim is that, well, if you take a number minus its complex conjugated, the real parts cancel and the imaginary parts sum. So actually what we have is that this difference gives me an imaginary complex number. Since all these are real numbers, what this number, whose real part is equal to 0, it's actually equal to 0, because all the other numbers are real numbers. So since this difference is equal to 0, what I indeed have is this identity. So up to now, I proved that identity where x plus and x minus are given by these expressions. So what I will do now is that I will erase everything and I will start from this identity. So I just erased everything and I kept the identity which we obtained, so that the norm square of ax is equal to 1/4 of this expression, where x plus is given by this sum and x minus by that sum. And what I'm trying to prove here is that the norm of A is bounded by m, where m is given by this variational expression. So here, now if you look at our definition from m, we see that ax plus x plus, it's bounded by m times the norm of x plus square. And the same thing happens to here. So here I get m times the norm of x minus square. Here, x plus and x minus may not have norm equal to 1, but it's clear that for all y, that this is bounded by m times the norm of y square, because if y is different from 0, I just divide that by the norm of y, and I get that y the norm of y the norm of y. This, because y divided by its norm it's a new vector which has norm equal to 1, so this is bounded by m. Now I can pass by linearity, I can remove, take y out of the scalar product as well as the norm of y, and I get this inequality. So this is what I'm using here to claim that this is bounded by 1/4 of m times the square of the norm of x plus m times the square of the norm of x minus. So this is what we have. And now let's recall what is x plus and x minus. So I continue here. So this is equal to m divided by 4 times the norm of x plus square, which is the scalar product of x plus with x plus. So this is lambda x plus 1 over lambda ax lambda x plus 1 over lambda ax. So this is the square of the norm of x plus the same thing for x minus. So this is lambda x minus 1 over lambda ax lambda x minus 1 over lambda ax. So now let's compute these scalar products. So I get lambda square, the norm of x square. Then these two terms, they give me, because A is symmetric, the lambda cancels with 1 over lambda, and what remains is 2 times ax x. So this gives me the cross terms, and then I have plus 1 over lambda square times the norm of ax square. And let's do the same thing to the second term. So again, I have here lambda x, which gives me lambda square, the norm of x square, plus the other term, which is 1 over lambda square, the norm of ax square. And then the cross terms, the lambdas will cancel. What I get is x ax, but a is symmetric, so I can put it on the first term, and I have a minus sign, so that will give me minus 2 times ax x. Because the cross terms are exactly the same, and I'm using here that a is symmetric to place this a in the other side. So now if you look at the expression we obtained, you see that the lambda square x square appeared twice, as well as the 1 over lambda square ax square, while the cross terms, they just cancel. So if I take the 2 out, this is equal to m divided by 2 times lambda square x square plus 1 over lambda square ax square. And here, remember, lambda, it's a real number, which is arbitrary. So what we obtained up to now is that ax square, let me write it here, it's less or equal than this expression. Remember, we have this less or equal, and here it's a sequence of identities. So that ax square, it's bounded by m divided by 2 times this expression. The left-hand side doesn't depend on lambda. The right-hand side depends on lambda. So I can optimize over lambda. So this is, so what I get from this inequality by optimizing over lambda is that ax square, it's less or equal than m divided by 2, the infimum over all lambda positives, and here if I take lambda square or lambda, it's the same thing, of lambda x square plus 1 over lambda. So maybe not to confuse, let me call gamma 1 over gamma ax square. Right? Just I'm replacing lambda square by gamma, and I'm minimizing, optimizing that over all positive gamma. And well, it's a very easy task to optimize the function gamma a plus 1 over gamma b. If a and b are positive, the infimum over all positive gammas of this expression is equal to 2 times the square root of ab. So I leave it to you to check this identity. And if I use this identity, what I get is that this is equal to m divided by 2. And then by optimizing that, I get a 2 square root of x squared ax squared. And so you see that the 2 cancel with the 2. This gives me m times the norm of s. But now let me recall that we started from x, which has norm equal to 1, times the norm of ax. So what we get at the end is that ax squared, it's less or equal than m times ax. So the conclusion from this computation is that ax squared, it's less or equal than m ax. And what I wanted to conclude is that what I needed to show is that ax, it's bounded by m. Right? I want to show that for all x whose norm is equal to 1, that ax, it's bounded by m. We obtain that inequality. Well, there are two possible cases. Either ax, the norm of ax is 0, in which case this inequality is trivially satisfied because m is non-negative, or ax is not 0, so the norm of ax is strictly positive, and therefore I can divide it by ax and get that inequality. So in either case, I obtain that the norm of ax is bounded by m. And since this holds for all x whose norm is equal to 1, what I proved is that the supremum over all x whose norm is equal to 1 of the norm of ax, it's bounded by m, which means that the norm of a is bounded by m, and this is exactly what we wanted to prove. So this completes this lecture, and in the next lecture, I will start to talk about symmetric compact operator.